Okay, so I want you to picture this. The entire complex plane wrapped around in a torus. That's what modular forms study. How atoms that live on lattices on the complex plane, symmetries are repeat in two directions. These transformations, called modular transformations, twist, stretch, and rotate the complex plane but somehow preserve this hidden structure. And modular forms are special functions that respect these symmetries. They transform in a very controlled way. At this point, you're probably wondering, where does 2 pi sneak in? In this case, we're going to introduce the letter Q, which is involved in the theory of modular forms and is used in number theory as well. That's right. Q equals e to the power of 2 pi I z. This is very important as it corresponds to how it is used in modular forms. This little exponential term shows up everywhere in modular forms, so that is why it is really important to consider it. And I'll explain why. So why 2 pi? Because it encodes a full rotation. When the imaginary part of z increases by 1, a basic step in the lattice, Q loops exactly once around the unit circle. Modular forms are often written as infinite power series in Q. The coefficients, the an, hold deep arithmetic secrets, things like partition numbers or even information about elliptic curves. In a similar manner, here's one of the most famous modular forms, the discriminant function. Its Q expansion starts with delta z equals Q minus 24Q squared plus 252Q cubed. And it goes on. So in this case, every coefficient is an integer, and everyone is whispering number theory. But why does 2 pi keep showing up? It's because the core symmetry of modular forms is about tiling the complex plane by translations and rotations. And rotations are measured in the complex plane by units of 2 pi. Think about it. Move z up by 1. Because e to the power of 2 pi I equals 1, so Q doesn't change. This matches the fact that modular forms are periodic in the horizontal direction. Modular forms aren't just periodic, they also have this magical flip. This swaps big numbers with small ones, infinity with 0. It's the symmetry of the lattice, and Q behaves very differently under it. As Q near infinity becomes small, Q near 0 becomes big. That's why the Q expansion is actually an expansion at near the cusp of infinity. As z goes up in the imaginary direction, Q shrinks towards 0, meaning the power series converges beautifully. And then there's the J function. It's like the king of all modular functions. Look at all these numbers. They seem random, but they encode symmetries that connect to, get this, the monster group, the largest sporadic single group. And every time it's Q, it's e to the power of I times 2 pi z doing the heavy lifting. It's because the modular world isn't about linear distance, it's about rotation, it's about windings, about how the complex plane loops back onto itself. The reason 2 pi shows up is that the modular world is secretly a world of circles. The space of lattices becomes a torus, a donut, and the donut is parametricized by how z moves around, which turns to Q winding around the circle. That's the secret. It's 2 pi. It's always been 2 pi. The full turn, the complete rotation, the natural unit of symmetry in the modular universe. And this is why modular forms connect to everything, from counting partitions to elliptic curves to string theory to the proof of Fermat's last theorem. It's because these symmetries, measured in full turns of 2 pi, are the deepest symmetries in mathematics. So next time someone tells you that pi is the most important number of mathematics, remind them, it's only half the story. The true heartbeat of mathematics is 2 pi.